Hello, and I welcome you to another session on data mining. Today, what we're going to cover is called support vector machines, which are another type of linear classifier, just like perceptrons. But we want to study them because they are better than perceptrons, and we have a theoretical proof that they are better than perceptrons. So that's why we're going to cover them. Some of you may have already studied these support vector machines, but what we are going to try to do is to try to build from the ground up the support vector machines. So specifically, we're going to try to transform a perceptron into a support vector machine. Before moving on, let me give you a quick recap of what we've been doing so far in this module. We've been doing binary classification, that is developing a machine learning model that classifies between two different types of object, let's say apples and oranges, based on their feature representations. So we're given a set of labeled training examples. In this case, on your screen, you can see 8 examples. Each of them is represented by two features, feature one and feature two. Let's say they can be roundness or redness, or you can extract 1,000 different types of features. I think now the concept of features is going to be you'd be able to understand the concept of features, and we can have a feature representation for a given example, and that can be pretty large. The goal of classification then is to find a mathematical function that uses these feature representations of each of those examples together with the known labels of each of those training examples to develop a mathematical function, or a discriminant as it is called, that separates the two classes in the training data set. So let's say if you use a linear discriminant, then you can classify everything above that particular line into the positive class and everything below that line into the negative class. We also talked about k-nearest neighbor classifiers that use distance of a given example, of a given test example, to assign a label to it based on its closest example in the training data. So let's say if you've got, let me turn on my pen here, please. And let's say if you got an example here that is given to you as a test example, then because we know that the closest example to this test example is an apple, so we'll be classifying this example as an apple. Okay, similarly, if an example is over here, then because the closest example to this test example is an orange in the feature space, therefore we'll be using to that information to label this as an orange or a negative class example. In terms of the linear discriminants that we talked about, those are functions that separate the data sets using a line. So we want to find a line that separates this data set, and that was the formation or the formulation or the basis of the formulation of a perceptron. Okay, so there's an important discrimination that I want to re-emphasize here, and that is, although we're given a training data set and we want to find a function that gives us the lowest error over the training data set, but that's not the whole of the goal. The real goal is that we should have a mathematical function that allows us to generalize to unseen cases. Remember, that has been the theme of this overall module right from the very beginning. Machine learning is learning from data to generalize, and that's what we are interested in. And this discrimination is going to be, or this subtle point is going to become very important in the discussion of support vector machines, as we shall see. If you at a higher level think, if you think at a higher level, then you can think of a classifier as a computational block that takes in as a feature representation x and spits out a single number. So it converts the feature representation x to a single number, which should be positive in case of a linear discriminant for positive examples and negative for negatively labeled examples. That particular computational block, called a classifier or a linear discriminant, has an internal representation. In this case, it's a representation based on W and B, which are two parameters. Uh, and we want to tune these values, the values of these parameters, these W and B, so that it does a good job on the training set. But remember, that's not the whole goal. The real goal is that we should be able to do well on an unseen test example as well. So if I give this particular machine learning model the features of an apple or an orange that was not part of this training set, it should still be able to classify it correctly, whether that is an apple or an orange. And that is the true test of the accuracy of a machine learning model. So at a higher level, uh, machine learning can be translated as learning from data to generalize, or essentially building the internal representation of the data to do that, of the classifier to do that. So we use the training data to to obtain these parameter values W and B or in case of a nearest neighbor classifier, we use the training data and we use a distance-based rule to assign labels to an unseen test example. But it does have an internal representation so that it takes in a classifier, the feature representation of an example as input, and it generates the corresponding prediction score or a prediction label at the output. Okay. Just a brief recap of what we've done for the perceptron. We'll be doing a breakdown of all machine learning models in this module into three components, those being representation, evaluation, and optimization. For the perceptron, so you can think of these as interview questions. What is the representation of a perceptron? The perceptron requires a representation of each object in terms of its features. So you get a feature vector for each object X, which can be D dimensions. D can be arbitrarily large. And you are given a training data set in which you have N of these examples. So that is the representation of the data that we are taking as input. Okay. And in terms of the classifier itself, we are restricting for the perceptron, we are restricting to linear discriminates. A linear discriminant can be represented by two sets of parameters. There's a weight value that is involved in the dot product with the input feature representation, and then a bias term is added to it. So the representation is based on two parameters or two types of parameters. One of them is the weight and the other is the bias, and it's a linear representation that allows us to convert the feature representation of a given example into a single number at the output. And once we have that representation, the way of converting the feature representation into a single number, we use that to calculate or to define what would be a misclassification or what would be an error for this machine learning model. So remember, we talked about the 0, 1 loss function, and that is one way of measuring error. So you can think of different representations of the perceptron and for a given data set, they would generate different errors or different amounts of errors. Some lines would classify some points in the training data set, others would misclassify others, and we want to measure how much error is there for a given training example, for a given line for the given data set. So we do that. We can do that using the Heinz loss function, which essentially flags errors whenever the sign of the discriminant function score f of x does not match with the label. So if it's a positively labeled example, so if y is equal to +1, but your f of x is less than 0, that means we want the object to be above the line, but if it's being classified as below the line, we have an error. And that is what this loss function does. So it measures how much error there is, or whether a particular example is in error by a given function f. And we can calculate the overall error by summing across the error of all of the training examples. So we can calculate the loss function over all the training examples that we have. We can use the Henge loss, we can use the 0, 1 step loss for that. And that is going to give a certain error for a given function. And I'm going to denote that by LF over here. And the goal then is to minimize that error. And we had studied how to minimize arbitrary functions. We can use our favorite algorithm of gradient descent that essentially we calculate the gradient of the function that we are interested in optimizing, and then we take a step in the direction opposite to the gradient, or we change the parameters of the function such that we get a reduced error in the next time step. However, that gradient descent algorithm being based on the calculation of the gradient imposes a certain constraint on what type of loss functions we can use, and the 0, 1 loss function does not satisfy those constraints. That is, it's not it's not continuous, so we cannot calculate its gradient at certain points, and then it's not convex. So the finding of the global minima of the optimization function is not guaranteed if we use the 0, 1 loss function. So those are the two problems associated with the 0, 1 loss function. And to solve that, we developed this Hinge loss function that flags an error whenever y times, which is the label, in f of x uh, is less than or equal to 1. And the amount of error is equal to 1 minus y times f of x. We had calculated that, so I hope you're familiar with that. If you're not, please go ahead and rewatch the formulation of the perceptron algorithm. So, so we have now a representation, a feature representation for the data, a linear representation for the discriminant function. We have a definition of the error function called the loss function, which tells us how much error we are getting for each example, and then we can calculate the overall error for all of the training examples by simply summing up the uh, individual losses for all of the training examples in our training data set. And we can do that. And once we have that, then what we want to do is we want to use gradient descent, and we want to minimize this loss function, and that gives rise to this beautiful algorithm that we talked about last time. It's a very simple algorithm that picks a certain example for which the label is known. It computes the discriminant function score, and if that particular example produces a loss, then what we do is we use gradient descent update to update the weights of the discriminant, and we get a new set of weights, and we keep on doing that until we are satisfied or we are bored. Okay, so until convergence, and we discussed the convergence criteria of the perceptron in the previous lecture. So that's a summary of what we did so far in this module. And then we also, of course, coded it up in Python, and we saw that it's a very simple piece of code. This is essentially a translation of the major steps uh, from mathematics into the code over here. Fortunately, we don't need to write the code ourselves every time. We can use the existing perceptron within the sklearn library. We can create an object of the perceptron, and we can fit a training data set to it, which is essentially going to give us the optimal values of weights and biases for that perceptron, and then we can use this predict function to determine labels of a given test example. So there's already a notebook available as part of this module that you can use to understand and implement perceptrons using either the sklearn library, or you can do it using your own code. You can free to modify that if you like. But if you think at a higher level, what we've done so far is we were given a training data set in which there were n examples. Each of those examples was represented by d features. So this gives rise to what we call a feature matrix or a data matrix of size n cross d. For each of those n examples, we know what the corresponding binary label is, whether it's +1 or -1. So we have got a vector called ytrain for which which consists of n values. Each value can be +1 or -1. That corresponds to the feature that is contained in this matrix X train. Now let's say we've got a function. Let's say we've got a classifier f. It can be any classifier, and for that particular classifier over this training data set, we can calculate how much error, classification error or misclassification error this particular function produces. So let's say to keep things simple, let's say if you got this training data set that's on your screen at the right, you've got a set of red examples, and then you've got a set of cyan examples, and we can have different functions, we can have different discriminants. Let's say all of those discriminants that we are interested in are linear. So this is technically called that we are focusing on a class of functions or a class of classifiers which are linear. So or we are focusing on linear discriminants. Then you can have about a billion different lines, and each of those lines is going to give you a different amount of error over this particular training data set. Let's say we've got this orange line over here, and I think you would now be able to say that this particular line is not a good approximator or not a particularly good classifier for this given data set, because it does not neatly partition this feature space into two parts. The same thing goes for this purple line, but for the red and the green line, both of those are okay because they give a training error of 0. So the goal of machine learning that we've been talking about so far is to find a function, an optimal function that minimizes the loss or the error as we measure it using, let's say, the hinge loss function or the 0, 1 loss function. We can have different loss functions, we can have different feature representations, we can have different function classes for the discriminants. So far, we have focused on two different function classes. One of them was the nearest neighbor rule, and the other one was the linear discriminant. The linear discriminant ones are based on a very simple representation. We have got f of x is equal to w transpose x plus b, which you would be bored with by now. But I hope you are also able to understand what this actually means. It simply means a way of transforming this feature representation into a scalar number. And what we want to do is we want to find a function. We want to find these weights and bias values, or we want to find the exact line, in other words, that gives us the minimum error. And that is mathematically represented by this optimization problem over here. So we want to find the weight values and the bias that gives us the lowest error over this particular training data set. And that's what we want. But that, as I started off this lecture, that is not the whole story. What we want to be able to do is to have a classifier that generalizes well to unseen data. However, so far what we have done is we've used only the training data and we've minimized the error or the loss only over the training data. And if you do that, then this process at a high level or in general, it is called empirical risk minimization. So what we are trying to do is to reduce the empirical risk or the error over the training data set. So another name for this ERM can be training data error minimization. Okay. And if we use this process, by EM I mean error minimization. Uh, so what that means, if we apply this process of minimizing the loss or the error or the risk, all of these mean the same thing for now. Uh, then what we want to do, or what we'll be able to do, is we'll be able to get this red line over here, or this green line that you can see on your screen. So we are learning only from training data. Now, the important point that I'm going to make, that we are going to try to understand in the rest of this lecture, is doing this is not enough. Doing this automatically does not guarantee generalization. If you minimize error over the training data set, that's good. But it's no guarantee that that particular classifier is going to generalize to an unseen test example, to all unseen test examples that it's going to get in testing that were not part of the training data set. To illustrate that point, I welcome you to walk with me as we try to understand this particular example that's on your screen. Let's say we've got a classification problem in which there are two features, x1 and x2. We've got a bunch of data points shown in red squares, and then you have got some cyan circles that you can see on your screen. Now, all of these lines, all of these beautifully colored lines, they are all equally good approximators or all equally good classifiers for this particular training data set. All of them produce an error of 0. Okay, so none of them is particularly better than anyone else for a given for this training data set. If you restrict our definition of machine learning to learn the training data set, then all of these are equally good. They give a training error of or an error over the training data set of 0. So all of these are equally good. There is no best approximator amongst all of them. So this is essentially the question on your screen: which separator is the best? Is a trick question if you limit your definition of best to the training data set only. But hold on a sec. Let's talk about something else. Let's focus on two of these lines, the red line and the green line. So the red line is this line on the left, and the green line is this line on the right. And both of them are equally good approximators of this particular training data set. Both of them give an error of 0, and both of them separate or linearly separate this particular data set. However, let's say and let's imagine a bit that this particular example that you see over here, okay, when you were calculating, let's say, the features of this example, the feature value along the first feature came out to be this much, and the feature value for this example along this vertical axis came to be this much, okay? And that's why this particular point is represented at the location where it is right now. However, let's say if you are, let's imagine that these features that you're calculating are obtained as a consequence of a sensor. Let's say you're using temperature of a particular patient to, to, to act as a feature to classify whether that patient is healthy or not. Now, if you use that temperature sensor is going to have a certain amount of error, or it may have a certain amount of error. I hope not, but it may. Let's say if you measure the temperature of this particular patient, let's call it patient X. So if you measure the temperature of patient X at one time, it comes out to be this particular value, and that's why we put this patient at this particular point in the feature space. Let's say if you measure that temperature at another with another sensor or with using the same sensor at another time, then this particular point can get displaced or its feature values can change, and that means that the point is going to shift, let's say, to this position in the feature space. Now that can happen if even for that particular patient that we have in the training data set. Okay, and now we know that this, let's say, this patient is belongs to the red class or is a patient of the negative class example in this case. Then if you follow this red discriminant rule, then because this new position of this patient, I'm going to call it X prime or X dash. I should put a better X prime here. So I hope you can see that. So if you imagine the patient over here, then this red line is going to classify it as a positive point, right? So just a small change in one of the feature values, either due to noise, due to measurement error, or whatever, is now going to result in the change of a label from negative to positive if you use this red discriminator. And that is a problem with this red discriminator. Okay, a small change in the input ideally should not produce a large change in the output. Small changes in inputs can happen because of, let's say, measurement errors, or there can be other types of errors that can cause small perturbations in this input feature space. So those should not change the output label, which it is doing for the red discriminator. So this is a problem. Let's say if we have this example represented in this animation and it's moved to this blue location, then that red discriminator now misclassifies this particular example. Okay. On the other hand, if you take a look at this green discriminator that you see, this green line, this one over here, then that appears to be a better approximator, or at least it's more robust over this particular training data set. If this position gets changed, if this patient's temperature recording is erroneous, the green discriminator will still be able to classify it as a negative example, and that tells me that it's more robust or it's more reliable. Now, strictly speaking, over the originally given training data set, both of these, this red and the green discriminator, are equally good. However, we've seen that one of them is more robust because it doesn't change its output due to a small change in the input. And that can happen due to measurement noise. So we can say that the green one is more robust. But there are some better there are other properties that are quite good about this green discriminator as well. So formally, we can say that the boundary that which lies at the maximum distance from data. Now, the reason the green discriminator is better is probably because it lies almost in between points of these two classes. Okay, so it's at the exact middle of the two. So the boundary which lies at the maximum distance from data points of both classes gives better tolerance to noise and better generalization. So I've talked about how it gives us better tolerance to noise, and we've seen that small changes in the input don't affect the labels produced by this green line as much as they do, as much as the labels that would be generated by this red line. But the second bit is more interesting, and that is why do you think this green line is going to offer better generalization than this red line? And I would welcome you to pause the video and think about it before proceeding to come up with an answer of your own. So, and I hope that you've been able to convince yourself that the green line is going to generalize better to unseen examples. But I'm going to help you or walk you through why that would be the case. Let's say during testing, we get a test example that is over here. Okay. Now, both the red and the green line are going to classify it correctly. And by correctly, I mean, I'll explain why I say correctly. but both of them are going to classify it as negative example. Now, if you see the data density or the density of data in this feature space, we see that there's a large density of red points that are close to this particular star that I just drawn as a test example. So because there's a larger density of red points there, probably this point is going to be classified, should be classified as a red point as well. And both of these lines, the red line and the green line, are able to do that. Okay. And this is an assumption we are making that test labels, test examples follow data density or the probability density of the training data. So that is an assumption that we are making here. If this assumption is true, then this particular red star is going to should be classified as the red point. And if that assumption is true, both of these red and the green line are able to classify it correctly. However, let's shift this star point a bit to the right. Okay, and if we follow this assumption that test examples should follow the data density of training data, then the red line no longer reflects that assumption. So it would generate a positive label for this particular example. Although this particular example, this star, this second star, so I'm going to just call it 2, is still closer to this red point than it is to this to these cyan points. So if we follow this assumption that test examples would follow data density of training data, then this red point, this red line is a worse or is not a good approximator of or not a good generalizer or a generalizable classifier for this particular classification problem. So I hope that you're able to understand the assumption that we are making. If we make the assumption that test examples follow the same data distribution as the training data, then this red line is no longer a good approximator because it's going to generate labels that probably don't reflect this. Now let's talk about why this is a reasonable assumption to make. Because if this assumption is not true, then we probably wouldn't be able to classify very correctly anyways. We need to, if the test examples are going to be very different from our training examples, then there is no way for us to generalize anyways. So this is a reasonable assumption to make at this point. And if we make that assumption, then the green line that you see is a better approximator than the red line. And what makes the green line a better approximator is that it's in between the two classes, so it classifies the two classes with 0% error, but it also is maximum distance away from the two classes. So it gives you what is called the maximum margin between the two classes. Okay, and that's what we are going to introduce the concept of margin next. If you're not still clear about this particular case, spend some more time on why this assumption, this is called, technically, this is called the smoothness assumption. Okay, or more precisely, it's called the independent and identically distributed assumption, IID assumption. Okay, and if this assumption is true, then this particular green line, because it has a larger margin, and we are going to define margin formally in just a second, is a better approximator than the red line. Okay, so let's talk about what exactly is margin. So we define the margin. You can think of it like this. Let's say if you got a linear discriminant, we've got a red linear discriminant in front of you, and then we've got a green linear discriminant in front of you. Then imagine that these discriminants are balloons, and if you start filling them with air, eventually they are going to swell up, and they're going to go ahead and touch one of the points of the two classes. So either it's going to get in touch with the point of the red class, or it's going to get in touch with one of the points of the cyan class. The amount of air that you can put in controls how much swelling how much the balloon expands over here. And the more the balloon expands, the more margin it has. Okay, so that's one way of conceptualizing this this word margin. And classifiers that have larger margin, they are more robust because they are more immune to small perturbations in the training data set, but small changes in the training data are not going to flip their labels, just like we saw. And the other thing is they are going to generalize better under the assumption, under the IID assumption, or the smoothness assumption that we just talked about. Okay, so more margin is better if that assumption holds, which is a reasonable assumption to make when we're talking about classification problems. Okay, so out of these two classifiers that you have on in front of you on your screen, because we can expand this green balloon, it's a it's a strange two-dimensional balloon, but we can expand it by an amount this much that we call as the green margin in comparison to this red point, which we can only expand so much before we run into one of these points, one of the points over here. Okay, so that is one way of looking at margin. Another way you can think about margin is that we keep the line at the same place, then how much can I move one of the points before of one of the classes before it occurs on the line? And the more displacement a point of either of the two classes requires for it to be able to touch the line that or the linear discriminant that we have, the more margin that linear discriminant has. Okay, so both of these are equivalent definitions. Both of those give you a hand waving explanation of what margin is. But formally, it's the width by which the linear discriminant, or just the error margin of a particular linear discriminant. The more margin a particular linear discriminant has, the more robust, as you can probably imagine by now, it's going to be to perturbations, and the better generalization it's going to give to unseen data. Because it's not going to, under the smoothness assumption, it's not going to misclassify a point that occurs here, whereas the red line can probably misclassify this same point into the positive class, although it should be in the negative class. Now, some people get confused by how do we know the labels of the test example? We don't. We are making an assumption here that the labels of the training data, the test data set is going to be distributed in the same way as the training data. And if that assumption is correct, which is a reasonable assumption, then this is the case. Okay. And this follows from the concept of rationality in artificial intelligence, that we have a given data set, we have got a view of the world in our case, in this case, and we want to make use of all the information that is given to us. So we want to make the use of the data that is given to us, but we can also impose certain other assumptions that are reasonable to make a more intelligent machine. So this is the main difference between perceptrons and support vector machines. A perceptron is not guaranteed to maximize margin, and as a consequence, it's not going to give you the best generalization. Whereas a support vector machine, on the other hand, is going to first of all try to reduce the error over the training data set, and then it's also going to give you the maximum margin. So if you think of perceptron and the support vector machine, it's more likely that the perceptron is going to give you this red line, whereas the support vector machine is guaranteed for this particular data set to give you this green line that you see, and it's going to be a better approximator. But we are going to try to develop a mathematical formulation that leads us to this green line, or the maximum margin line as it is called. So before moving on to more mathematical parts, let's try to understand it in a bit more intuitive manner. So margin, as we talked about, so classifiers with large margin have a property. And out of these two lines that you see on your screen, the red line on the left and the green line on the right, the red line has lesser margin in comparison to the blue line. And we've talked about that, why that is the case. So I hope you are able to understand that. But the red line, we would say, has a small margin. Let me just write that down, small margin. And the green line has a large margin. Okay. But we are going to relate it to another concept in machine learning, which is very important, and that is called regularization. Remember, we were talking a bit earlier about a small change in the input can, let's say, due to a measurement error, can cause this point, this red point, to shift a bit into this blue point. And now, although our smoothness assumption is there, or under the smoothness assumption, this red line is going to misclassify. So originally, this point that we were taking was below the line, but now because of that small error, it's going to be above the line, and the discriminant function is going to classify this as a positive class example because it's above the line. Okay, so a small change in the input to this discriminant, to this red discriminant, has caused a large change or a change in the label assignment. Okay, so this should not be the case. If you want to develop robust systems, then what we really want to do is a small change in the input should produce only a small change in the output. And it should only change the output when it's relevant. Okay. So if for example, an example is on this right side, then it should produce a positive label, but otherwise it should not produce a positive label. So I'm going to say this, that a small change, so it's already written here, small change in the input X of this computing block or a classifier should cause small changes in the output. Okay. And if that is the case, we say that the system, or in this case, the classifier, is well regularized. So it has high regularization. And if that is not the case, then it has low regularization. So small margin means low regularization as well. Okay, so I hope you're able to understand that concept. And large margin means that it has high regularization as well. For a linear classifier, it's really easy for us to understand what regularization means. Remember, a linear classifier produces its output by multiplying each feature x1, let's say, with a corresponding weight w1, and adding it to the product of w2, weight w2, with feature x2, and so on. Or in other words, we take the dot product. That means if the weight of a particular feature, let's say W2, is large, then a small change in this feature is going to produce a large change in the output f of x. I hope you're able to understand that. It's just proportionality. A small change in x2, given that W2 is large, is going to produce a large change in f of x. So that means in order to enforce regularization, which we want, because we want robustness and because we want large margin, we want these weights to be, and I'm going to pause here and you can pause the video and answer. Should these weights be large if we want high regularization, or should these weights be small if we want high regularization? Okay, so you can pause the video and answer it. And the answer is pretty simple. The magnitude of the weight of a particular weight, let's say Wi, should be small. And if it's zero, let's say, then even if I change the input, the corresponding input, the output is not going to change because the corresponding weight is zero. But if the weight, the absolute value of the weight is large, either it's positive or negative, let's say if it's equal to 1000, then a very small change in x is going to produce a large change in the output, right? So if, for example, the weight is plus 1000, then a small change in x by a factor of zero point 0.1 is going to get multiplied by this 1000, and it's going to produce a large change in the output then. And if it's minus 1000, the story remains the same. That's why the absolute value of this weight matters. Okay. So a small change in the input is going to produce a small change in the output if the weight is going to be small. A small change in the input is going to produce a large change if the absolute value of the weight is going to be large. So ideally, we want our classifier or the machine learning model or the linear discriminant that we are developing is to have small weights. So you want to build a classifier that now has two requirements. First of all, it should be able to classify between the positive examples and the negative examples. much like the constraint satisfaction problem that we solved. Everything in the positive class should be above the line, and everything in the negative class should be below the line. But that does not guarantee that we would get maximum margin or we would get high regularization. To be able to do that, we need to introduce another concept, and that is we want to introduce another desirable criteria, and that is the weights that we get. The weights that get multiplied with the features of the given example, they should be small. So what we've seen so far is if you want to do error minimization over the training data set, a perceptron algorithm is able to do that. However, we've seen that the perceptron algorithm can lead to small margin that can give you, uh, that can result in poor noise tolerance due to errors in measurement, and it can also give you poor generalization over an unseen test example. And to fix that, what we need is we need good or high regularization or a larger margin equivalently. And to do that, we also need these weight values to be small. So we now have two criteria. One of them is covered by what is called the empirical risk minimization criteria, that we should minimize the training error over the given training data set, which is fine. But it should do something more than that. And that something more in this case is called we should do regularization. This concept of regularization plus empirical error minimization was first proposed by this excellent scientist called Vladimir Vapnik in the 1960s. He wrote a book called The Statistical Theory of Learning. And that's a pretty deep statistical book that covers how much error you can expect over a given test set if you use a certain type of classifier. Okay, we're not going to go into the theoretical details of this in, into too much detail of that in this particular module. But what I want you to understand is what this person said or what this scientist said, and he said that empirical error minimization is not going to guarantee good generalization or good noise tolerance over unseen test sets. And we saw that through various examples in the previous 2 or 3 slides that we've been talking about. He said that we should be doing something more over and above empirical risk minimization. We should be doing regularization, and that thing that we want to do two things. One, empirical error minimization plus regularization is called structural risk minimization. And this is the idea that he introduced, which forms the theoretical basis of support vector machines. And next, what we are going to do in the next slides, we are going to talk about how this idea is represented mathematically, or how can we develop a mathematical representation of structural risk minimization. So I welcome you to pause this video, stop this video here, think about what we've covered so far, think about specifically why uh, empirical error minimization or learning only from training data is not enough. Why do we want to do margin maximization, or why do we want to do regularization? Build an intuitive understanding of that so that we can then step into the mathematical formulation of structural risk minimization, which will lead us to a support vector machine. Okay, so thank you.